Related rates, the basics. Alright, so before we look at some detailed examples, I want to try to help you understand the concept of related rates. So let's imagine this is your house, and this is where you and your parents leave from in the morning. And let's imagine you leave at the exact same time. So this is your starting location. You are here at time 0. And let's say that you head east to school. So here's school, and here's you in your car heading east. And your parents, they leave at time 0, but they head south to work. And let's say 10 minutes later, I could tell you exactly how far you are from your house. So this moment in time is when t equals 10 minutes. And let's say at 10 minutes, you are exactly 4 miles from your house. And I'm going to go ahead and call that distance x. And then let's say at time t equals 10 minutes, we could figure out that your parents' distance from the house was 3 miles. So let's go ahead and say the distance from the very back of the car. So let's just try to make it really specific. So at 10 minutes, you are 4 miles from the house. Your parents are 3 miles from the house. Now, if I was interested in finding the distance between the two of you, between you and your parents, the straight line distance, I could connect these two dots together. And to find that distance, I could recognize that because your parents are heading perfectly south and you're going perfectly west, east, this forms a right triangle. And so to find this distance, let's go ahead and call it z. I could use the Pythagorean theorem. So I'm going to go ahead and call this y. The Pythagorean theorem would tell me that x squared plus y squared equals z squared. So this Pythagorean theorem is a way to relate distances. So if I were interested in finding the distance, so this hypotenuse of the Pythagorean theorem, I could plug everything in. So x is 4, y is 3, and I'm solving for z. So this is 25. So taking the square root of both sides, I would get plus or minus 5. But since z is a distance, z is just positive 5 miles. So notice I had a known geometric equation that allowed me to relate two distances together using a right triangle's geometry formula, the Pythagorean theorem. But at 10 minutes, not only can you tell exactly how far you are from the house, let's say, and exactly how far your parents are from the house, let's say right at 10 minutes, we looked at the speedometer. And we knew exactly how fast you were going at 10 minutes. So if right at 10 minutes we looked at the speedometer and you were going 40 miles per hour, so what that would translate to mathematically, and I'm going to change colors here, is that at this moment in time, you were traveling at a rate, so since this distance is x, the rate at which x is changing, the distance from the house right at this moment, the rate that the distance is changing is, we said, 40 miles per hour. Or miles per hour could be thought of as miles over 1 hour. So this is clearly a rate. And right at exactly 10 minutes, I could also figure out exactly how fast your parents were going. If we call this distance from the house y, then they are traveling at a rate of dy dt, which we just said was 30 miles per hour. So if we can find the exact rate of change that you were traveling at 10 minutes and the exact rate of change your parents were traveling at 10 minutes, then we can find exactly how fast the distance between you two is growing. So not how far apart you are. How far apart you are isn't a calculus question. That's a pre-calc question. That's using the Pythagorean theorem. So at 10 minutes, I know that you're 5 miles apart. But the question would be, how fast is the distance between you changing? What is the rate of change of the distance between the two of your cars? So in other words, the question that we're going to be asking is, what is dz dt at 10 minutes? This is the notion of related rates. We're trying to relate two rates together using known geometric formulas. So we can already relate distances using the Pythagorean theorem or other known geometric formulas, but now we want to go one step further and relate the rates of change at particular moments in time. So I would have to know exactly how fast you're going and exactly how fast your parents are going right at 10 minutes in order to be able to figure out the rate of change of the distance between the two of you. So this is what our goal is going to be in this section on related rates. All right, now let's go over the general strategy for solving a related rate problem. So the first step, of course, is to read the problem carefully, and you'll typically need to go through it at least twice to get all the relevant information out. So once you've done that, the best thing to do is to draw a diagram or a picture, and this is typically going to be a geometric shape of some kind. Part 3, once you've drawn your picture, you want to assign variables to all quantities that are changing and label all constants in the picture. So not everything is going to be a changing quantity. So when something is changing, we're going to have to label it a variable like x or y. But sometimes things will remain constant, a constant height or constant length, and then we can just go ahead and fill in that constant number in the diagram that we've drawn. Step 4, write the givens and the wants in mathematical notation. So these will likely be rates of the form dh dt, dr dt, d theta dt, dy dt, etc. So often we are given a rate of change expressed in words, and we have to translate that into mathematical notation of this form. So d something dt, and then we need to figure out what we want. What are we being asked for? And we might also be given constants, not only rates. So constants would be of the form x equals, r equals, or h equals. So we really have to distinguish between whether they've given us a quantity or a constant versus a rate. So those keywords like per, in, or for are going to tell us we've been given a rate. Number 5, write a general primary equation that relates the variables in the problem. And here you will likely be using geometry or trigonometry. So we want to somehow write an equation that relates the variables. So like in that previous example, we went to the Pythagorean theorem that was a known geometric formula that related the sides of a right triangle. So this is typically going to be one of the harder parts of the problem, is figuring out how to relate the variables so that we can eventually take its derivative. Now, part 6, if any quantities in the equations are constant, then you may replace the variable with the constant number. So if you haven't already labeled the constants in the picture, you can replace any variables with constants if those are not changing quantities. Otherwise, leave all the variables in the equation. And then this is sort of a little 6a or a side note. You may need to use geometry to manipulate a formula to eliminate an unwanted variable by substitution. So this gets into a trickier type of related rates problem where maybe you have one too many variables and you don't have enough information, so you have to use geometry or other tactics to get rid of that variable that you don't have any information about. Number 7, use the chain rule and implicit differentiation to differentiate both sides of the equation with respect to time. So once you find the equation, then it's a matter of correctly applying implicit differentiation, and in part 8, we substitute in the given data. So you found your givens in part 4. So once you take the derivative, you substitute in your givens and you solve for whatever you wanted, whatever that unknown quantity is. And then step 9, round your answer to 3 decimals, include units, and make sure your answer makes sense. So in calculus, we need to always make sure that we go out to the thousandths place. So what I mean by 3 decimals is 3 places past the decimal. We always have to include our units. And then you want to make sure your answer makes sense. So I always give the example of sometimes I have students say the car was traveling 450 miles per hour. So that definitely doesn't make sense. So once you're done, and you box in your answer, you go back and reread the question again and make sure that in the context of the problem, your answer makes sense in the real world. Alright, now let's look at a pretty basic example. Example 1, the sides of a square are increasing at a rate of 2 inches per minute. Part A, how fast is the area of the square increasing when the sides are 3 inches? So let's go back to the problem, the sides of a square. So the first step, if possible, is to draw a diagram, and the geometric shape is a square. So let's go ahead and draw a square, and a square has equal side lengths, so I'm going to call the side lengths S. And we're told that the sides of a square are increasing at a rate of 2 inches per minute. So once we've drawn our diagram and we've labeled our diagram with variables, so the side lengths are changing, they both need to be variables, so S and S, the same variable because it's a square. Now I want to label my givens. So what I've been given in this problem is a rate. The side of the square is increasing at a rate of 2 inches per minute. Well, I called the side of my square S. So in mathematical notation, I have been given ds dt. The rate of change of the side with respect to time equals 2 inches per minute. So I wanted to translate my given information in words. So I know I was given in words the side of a square is increasing at a rate of 2 inches per minute into mathematical notation. So I want to identify the givens and the want. So what do I want to find? In part A, how fast is the area of the square increasing when the sides are 3 inches? So I want the rate of change, because I'm asked how fast, the rate of change of the area of a square. So we denote area with the variable A, so I want dA dt. I want the rate of change of the area with respect to time when the sides, when S equals 3 inches. That's what I want. So I wrote my givens and my wants. So the next step is to find an equation that relates the variables. So my variables are A and S, area and side. So the area and the side relationship in a square is that area equals side squared. So once I write the equation, if possible, I fill in any constants. Well, the variable A is not a constant, it's changing. The area is changing because S is changing as well. The side of the square is changing. So I cannot replace either A or S with a number yet. They are both changing quantities. So at this step, I have to take the derivative with respect to t of both sides. So d dt of A and d dt, the derivative with respect to time of S squared. So now, this is implicit differentiation. The variables here don't match. So the derivative of A would be 1, but since the variables don't match, I need to include dA dt equals, so now here the variables don't match. The derivative of S squared is 2S, but I also need to include a ds dt. So I wanted dA dt when the side is 3 inches. So I'm about to plug 3 into this S right here, and I'm given ds dt is 2 inches per minute. So in other words, dA dt is 2 times 3 times 2. So I'm filling in my S, which was 3 inches, and my ds dt, which was 2 inches per minute. So what I also want to do here is I want to include units. So the 3 inches had the units of inches, and my ds dt had units of inches per minute. So this is inches times inches per minute. So in other words, the final answer would be, well, I multiply all my numbers, so 2 times 3 times 2 is going to give me 12. So my answer is going to be 12, but my units, well, this is inches times inches, so this is like inches over 1. So inches times inches is inches squared per minute. So that should make sense because I wanted the rate of change of an area. Let's remember an area is a unit that's squared, so inches squared, over a time, which is in minutes. So the rate of change of the area with respect to time, exactly when the side length is 3 inches, is 12 inches squared per minute. So that is dA dt. So now let's look at part B. How fast is the area of the square increasing when the square has an area 25 inches squared? So I still have the same given. So my given, again, I'm just going to put G, is ds dt is 2 inches per minute. And I still want to know how fast the area of the square is increasing. So I still want dA dt, but what has changed is I want dA dt when the square has area 25 inches squared. So dA dt when the area A is equals 25 inches squared. So previously I was told I want dA dt when S equals 3 inches. This time I want dA dt when A equals 25 inches squared. So I in fact have to use the same relationship because I want dA dt, so A equals S squared. So I'm actually going to use the exact same formula, dA dt equals 2S ds dt. But I'm going to be missing something. I'm going to be missing an S. So I have a ds dt still. That quantity has remained 2. But I don't have a side length. I have an area. But if my area is 25 inches squared, I know that area is the same as side squared. So if area has to be 25 inches squared, then sine squared has to be 25 inches squared. So if I take the square root of both sides, I'll get S equals plus or minus 5, but since this is a distance, it has to be positive. So S has to be 5 inches. So in being given the area was 25 inches squared, that's like being told that the side length had to be 5 inches, because side squared, 5 inches times 5 inches, is 25 inches squared. So I can now take this quantity of 5 inches and substitute it into my side S. So my units will again be inches, that corresponds to 5, and then inches per minute, that corresponded to 2. So now I'm going to have 20 inches squared per minute. So how fast is the area of the square increasing when the square has area 25 inches squared? That's the same as like saying when the side of the square is 5 inches. So our answer there is 20 inches squared per minute. All right, example 2. The radius of a circular oil spill expands at a rate of 3 meters per minute. Part A. How fast is the area of the oil spill increasing when the radius is 45 meters? All right, so the radius of a circular oil spill. So the geometric shape we're dealing with is a circle. We have a circular oil spill. So let's just go ahead and draw a circle. And we're going to go ahead and draw its radius because we're being told information about the radius. So we want to label all of our variables. So our only variable here is r. And we're told the radius of the circular oil spill expands at a rate of 3 meters per minute. So what have we been given so far? That the radius expands at a rate, so dr dt expands, so this is going to be a positive quantity. That word expands would imply this is a positive 3 meters per minute. So now we need to figure out what we want. How fast is the area of the oil spill increasing when the radius is 45 meters? So I want the rate of change of the area. How fast is the area? So I want dA dt when the radius is 45 meters. So when r equals 45 meters. So now we have to come up with an equation that relates my radius and my area of a circle. So the area of a circle, A equals pi r squared. And if possible, I fill in any variables with constants if they are not changing. But in this oil spill, the area of the circular oil spill is going to be increasing because the radius is expanding at a rate of 3 meters per minute. So the radius is increasing, so it's changing. The area is thereby changing, so I cannot fill in any constants at this step. So now I take the derivative with respect to t of both sides, so ddt of a and ddt of pi r squared. So d dt of A is going to end up being dA dt. And then the derivative with respect to time of pi r squared. So pi is just a constant, so that's just going to stay there. So r is the variable, but r doesn't match t. So I'm going to have to apply the power rule to r squared. So the derivative of r squared is 2r. So I'm going to write that as 2 pi r, because I'm just bringing that constant pi down with me. So the derivative of r squared was 2r. And then I need to include a dr dt. And if you forget the dr dt, but you properly labeled your givens, then you'd go back and hopefully remember to include it, because now you have this given piece of information that you wouldn't have used. So I'm in search of dA dt when r is 45 meters. So dA dt is 2 pi r, which is 45, and dr dt is 3 meters per minute. So the number there's 3. My units of 45 were in meters, and my units of dr dt are in meters per minute. So my final answer is going to be 270. So I'm multiplying 2 times 45 times 3, or 90 times 3. And my units are going to be meters squared. So m times m is m squared per minute. So how fast, oops, and I lost the pi. The pi should be there. I can't forget that constant. So 270 pi meters squared per minute. So that's how fast the area of the oil spill is increasing right when the radius is 45 meters. So 270 pi meters squared per minute. So now in part B, if the radius of the spill is 0 at time 0, so all that means is that at time 0, nothing has spilled yet, so the radius can't be anything quite yet. How fast is the area increasing, so I want dA dt again, after 5 minutes has passed? So we can rewrite our given, it's the same thing, dr dt is 3 meters per minute, but my want is I want dA dt when 5 minutes has passed. So 5 minutes has passed. So this one is a little bit trickier. If I want dA dt, I still have this relationship here. So there's no need to differentiate again. We know this is the way we're going to find dA dt somehow relating the radius. So this is where we're at. We have dA dt equals 2 pi r dr dt. So we have dr dt. That's not a problem. We have 3. So what we then need is we need the radius. So I'm going to leave a blank space for the radius, but dr dt is 3. So I have to find the radius when 5 minutes has passed. So let's go back to the original problem. The radius is expanding at a rate of 3 meters every minute. So every minute that passes, the radius expands 3 meters. So at time 0, the radius is 0. At time 1, the radius must be 3 meters. At time 2, must be 6. At time 3, 9. At time 4, 12. So after 5 minutes has passed, I would be up to 15 meters. So when 5 minutes has passed, r must equal 15 meters, because the rate of change of r, so dr dt, is 3 meters every 1 minute. So that's how I'm getting that 15 meters out. It's because I have to understand that concept of the radius expanding 3 meters every 1 minute. So that means the radius that I'm plugging in here is 15. So now multiplying all my constants, this is going to be 90 pi, and then the units are still going to be meters squared because it's area per minute. So 90 pi meters squared per minute after 5 minutes has passed is going to be the rate of change of the area with respect to time. Okay, let's move on to a third example. The radius of a spherical balloon is decreasing at a rate of 2 inches per second. Part A, how fast is the volume of the balloon decreasing when the radius is 5 inches? Alright, so the radius of a spherical balloon, so we're talking about a sphere, so if possible we draw a picture. My 3D pictures are not spectacular, so sorry. Alright, good enough. So it's supposed to look like a sphere, and we're interested in labeling the radius. So the radius is going to be r. And we're told that the radius is decreasing at a rate of 2 inches per second. So we want to write down our given. We've been given dr dt is negative because the radius is decreasing at a rate of 2 inches per second. So given dr dt is negative 2 inches per second, we want to know how fast the volume, so I want the rate of change of the volume, we usually call volume V, so we want dv dt when the radius is 5 inches. So dv dt when r equals 5 inches. So now we write an equation that relates our variables. Our variables are V and R. The volume of a sphere is volume equals 4/3 pi r cubed. So pi is a constant, 4/3 is a constant, so my only variables are V and R. Both are changing. The volume is going to be changing because the radius is decreasing. So once we have this formula, we can't plug in any numbers for V and R yet. Now we take the derivative with respect to both sides, with respect to t of both sides. So ddt of V and ddt of 4/3 pi r cubed. So ddt of V would be 1 dv dt, so just dv dt. And now the derivative with respect to time of 4/3 pi r cubed. So r cubed is the variable. So the derivative of r cubed is 3r squared. So 3 and 4/3 would become 4. And I'm just going to bring down the pi. And we just reduce the exponent by 1. So 4 pi r squared. And then we need to include dr dt because this is implicit differentiation. Okay, so now we want dv dt when r is 5 inches, so I'm going to plug 5 into this r, and then negative 2 inches per second into dr dt. So 4 pi, and then r is 5 inches, and I'm actually going to put inches in there so I can emphasize the units, and then dr dt is going to be negative 2 inches per second. So this is 4 pi, 5 inches squared. Well, the 5 gets squared to be 25, but inches get squared as well. So I have inches squared, and then I have times negative 2 inches per second. So now I have 4 times 25 times negative 2, so that's going to be negative 200, multiplying the numbers without pi. So now I can just include the pi. And now I have 3 copies of inches, so inches squared and inches, so this would be inches cubed over seconds. So dv dt is negative 200 pi inches cubed per second. And we needed the top units to be in terms of volume, so volume is inches cubed over time in seconds. And dv dt needs to be negative because the question asked how fast is the volume of the balloon decreasing. And we had a decreasing rate here as well. So we did need our final answer to be a negative quantity. Alright, so now part B. When the volume of the balloon is 20 inches, what is the radius? So let's read that again. When the volume is 20 inches cubed, so when V equals 20 inches cubed, what is the radius? So I'm being asked for, I want just R. I want the radius. So this is actually not even a calculus problem, and it's really an understanding the difference in what you've been given. So when the volume is 20 inches cubed, so that's what I've been given. Oops, this is what I've been given. That volume equals 20 inches cubed. I want the radius. So I still have to come up with an equation that relates to the sides, or the information, 4/3 pi r cubed. But now all I need to do is substitute in 20 into V and solve for r. so 4/3 pi r cubed. So I'm just going to multiply both sides by 3/4. So this is going to be 60 over 4, which is 15. So 15 equals pi r squared. So I'll divide both sides by pi. So 15 over pi equals r squared. So if I want r equals the square root of 15 over pi. And it would be plus or minus, but because the radius is positive, it's just going to be the square root of 15 over pi. And the units of my radius are going to have to be in inches. So radius is just the 1 unit of inches. So r would be the square root of 15 over pi inches. And this problem is really just to illustrate the difference in being asked for a rate. So in this problem, how fast is the volume of the balloon decreasing, versus here, what is the radius? Not how fast is the radius changing or what is the rate of change of the radius, just what is the radius. So I would want that to be in units of inches. Alright, example 4. The radius of a circular cone of fixed height 30 centimeters is increasing at a rate of 3 centimeters per second. How fast is the volume increasing when the radius is 8 centimeters? So we've reached a trickier example now. The radius of a circular cone. So let me attempt to draw a circular cone. That's the shape, that's the geometric object. So a circular cone, trying to draw like an ice cream cone looking thing. So the radius is going to be this distance here. This is r. And this cone has a fixed height. So the height here is 30 centimeters. So that's the height. So the radius of the cone with fixed height is increasing at a rate of 3 centimeters per second. So this is like an extended sentence here, and that's where students get confused. But we're being told that the radius of the circular cone is increasing at a rate of 3 centimeters per second. So what have we been given? We've been given dr dt. The rate of change of the radius is 3 centimeters per second. And we're being asked to find, we want, how fast is the volume increasing when the radius is 8 centimeters. So I want the rate of change of the volume. How fast is the volume changing when the radius r equals 8 centimeters? So now I have to relate the variables. Well, the volume of a circular cone is V equals 1/3 pi r squared h. Alright, so I have 3 different variables here. And now I want to talk about, once you write the equation, if possible, you want to substitute in any quantities that are constant, that are not changing. So the volume of this cone is changing. So what's happening? Let's think about what's happening. The radius is increasing. So this r, imagine this ice cream cone is getting fatter. So the radius is expanding. So this ice cream cone is getting wider. But we were told that the height is not changing. The height is always going to be 30 centimeters. Well, if the radius is expanding, the volume is expanding. So I cannot replace v with anything. V is changing. I can't replace r with anything. R is a changing quantity. The radius is expanding. But the height, that's never changing. The height is always 30 centimeters. So that's a constant quantity. So I can replace h with 30. And once we do that, I'll explain why we would have really needed to do that and why it would have made our lives a lot harder to not have done that. So if we didn't replace h with this fixed number 30 here, when I took the derivative with respect to time of both sides here, the derivative of v, that's dv dt. But if I were to take the derivative over here on the right side, r squared and h are 2 separate functions. So I would have had to use the product rule along with implicit differentiation to differentiate this. And when I differentiated h, I would need dh dt, which isn't explicitly given, and it would make our lives a little harder to think about. So at this step, when you find the equation, if there's any quantities that are not changing, we can replace them numerically instead of using the variable. So now let's rewrite this. Volume equals 30 times 1/3 gives me 10. So 10 pi r squared is a lot easier to deal with. So now I take d dt of both sides. So d dt of v and then d dt of 10 pi r squared. So I'm going to go ahead and bring the work up here. The left side is dv dt. And the right side, r is the variable. So the derivative of r is 2, or r squared is 2r. So times 10, that's going to be 20 pi r, and then we need to include the dr dt for implicit differentiation. And now I wanted dv dt when r was 8. So dv dt is 20 pi, this is an r, whoops, this is an r. So my r was 8 centimeters, and then dr dt was centimeters per second. So 3 centimeters per second. And the 30 actually came with the unit centimeters. So that's where our extra centimeters is going to have to come in to play. So this 20 actually had a unit of centimeters as well. So multiplying all of my numbers together, I'm going to have 24 times 20 times pi. So 480 pi. And then I have centimeters cubed per second. And I needed centimeters cubed. That's why I went back to make sure that I didn't really lose a unit. I just forgot to carry it over with this 30 centimeters of height because I need this to be a volume. So centimeters cubed is a volume over my time in seconds. So 480 pi centimeters cubed per second is the rate of change of the volume with respect to time exactly when the radius is 8 centimeters. Alright, example 5. The height of a rectangular prism with a square base of side length 5 inches is growing. How fast is the height increasing when the volume of the prism is increasing at a rate of 200 inches cubed per minute? So this one's kind of tricky. The height of a rectangular prism with a square base. So I'm going to attempt to draw a rectangular prism with a square base. Alright, close enough. So we have to make sure that this prism has a square base. So they're the same sides along the, or same side lengths along the base, and we're told that those side lengths are 5 inches. So this side length S is 5, and this side length S is 5, but the height of this prism, this height is growing. So the height of a rectangular prism with square base of side length 5 inches is growing. So from all that, the height is growing. So just kind of that extended sentence. So in the question, how fast is the height increasing? So what do I want? I want to know how fast the height is increasing. I want dh dt. When the volume of the prism is increasing at a rate of 200 inches cubed per minute. So what I'm given here is I'm given that the volume of the prism is increasing. So I'm given dv dt is increasing at a rate of 200 inches cubed per minute. And another way to know that this was volume is the units, inches cubed. So how fast is the height increasing given that the volume at that particular moment is 200 inches cubed per minute? So now I have to come up with a formula that relates the side length. So in general, the volume of a rectangular prism is length times width times height. So in this case, it would be S times H, because the length and the width are the same if the base is a square. So it would be S squared H. But we're told that the side lengths are 5, and they're not changing. We're only told the height is changing. So I can substitute 5 into the S. So 5 squared H equals the volume of this rectangular prism, or V equals 25H. So this is one of those scenarios where I can plug in a constant for one of the variables because the side lengths of the base are unchanging. So now I need to take the derivative with respect to t of both sides. So d dt of v and then d dt of 25h. So now the left side is dv dt, and the right side, so the derivative of 25h is just 25 dh dt. So I'm in search of dh dt. So I have a quantity for dv dt. It's 200 inches cubed per minute. So let me go ahead and sort of bring the work back over here. So dv dt is 200, and that has to equal 25 dh dt. So if I want dh dt, I just divide both sides by 25. So 200 divided by 25 is 8. So 8 is the rate of change of the height. 8 is dh dt, and the units have to be inches per minute, because height is only one of the three components of the volume. So length times width times height. So the side length, this was in inches, this was in inches, so the height has to be in inches. So the rate of change of the height is in inches per minute. So dh dt is 8 inches per minute. So at this time, I hope that maybe if there was one or two that weren't 100% clear, that you go back and watch them, because these are considered to be the more basic examples of related rates. So you want to make sure and have one of the goals to set for yourself to be to identify the given and the want in the problem so far, and try to be able to find that equation that relates to two variables. So if this means going back and studying all of your geometric formulas and volume formulas, area, Pythagorean theorem, etc., those are all need to know information in order to get started on any of these problems. So hopefully you'll take the time to really understand these, because the next lesson we'll get into questions that are more likely to show up on the AP exam, which are a little bit harder in difficulty than the ones that have been presented here.